Welcome back. In the previous problem, we were looking at our fence that was kind of a rectangle with 12 little areas interconnected. And we talked about the minimum amount of material. And we were able to figure out that we need 438.2 total feet of fencing. We're now going to take that same problem and ask a different question. So there's our diagram from before. We're going to say, okay, so here's the situation. The external walls will cost $4 per foot, but the internal walls have to be more expensive because perhaps we have some wild animals that we're putting in these fence-in areas, and we want to make sure that they're strong enough so the animals can't attack each other, hurt each other, and whatnot. So they cost a whole lot more. So our question is, what dimensions will minimize the cost now? So now we're not looking at minimizing materials. In the problem before, we minimized materials, everything cost the same amount. So we just took the minimum amount of materials times the cost, and we got our answer. But here now, the two pieces of our wall cost different. $4 per foot for the external walls, the walls around the outside, $14 per foot on the inside. So we need to come up with a relationship between costs. Now, we still have, well, we'll come back to our area that's still going to be the same as it was before. X times Y is still going to be 200 square feet. So we first have our $4 external walls. So I've highlighted those in blue on the chart. And then realize what we have there on external walls. X is happening, 4 of them here and 4 of them over here, so 8 of them. 3 Y's up here and 3 Y's down here. So that external walls are going to get multiplied by the $4 cost. Okay, we then have our $14 internal walls. Okay, our $14 internal walls. So that's all the inside ones. And you can see, if you look at the X's, you have 4 coming down here and another 4 coming down, so it's 8X. The Y's, you have 9 of them. 3, 3, and 3 coming across. And they're all going to be multiplied by 14. And that's going to be my cost function. That's going to be my cost function. Now we want to clean that cost function up. We want to get a nicer looking cost function. So C equals, well, we're going to have 4 times 8x will be 32x, plus 14 times 8x will actually give us 144x. And then we're going to have 4 times 6y plus 14 times 9y. That's going to give us plus 150y. Plus 150y. Okay, and then we can take that answer and use that just like we did in the problem, the previous problem. So we still know that y is going to be 200 over x. So when we put that in for y, 200 over x, you're going to get 150 times 200 is going to be 30,000. It's over x, so it'll be x to the minus 1. Process now pretty much mirrors the last problem. We do our derivative. We want to know when is our derivative 0. So to solve that, we would have to, again, multiply both sides by x squared. Get 144x squared minus 30,000 equals 0. And we solve for x. So we bring the 30,000 over, divide by 144, and take the square root of both sides. And that gives us x equals 30,000 over 144, and the square root will give us 14.43. We also have to ask, when's it undefined? It's undefined at 0. It's undefined at 0. Now, we still need to verify, is that a minimum? Is that a minimum point? That 14.43. So we have to compare that with the derivative. Is it a minimum? And you should verify that. Pick a value smaller than 14, like 1. Obviously, this thing is negative. pick a value bigger than 14. Again, x equals 100 would be a great one here because that's 10,000 when you take 100 squared. 30,000 over 10,000 is 3. 144 minus 3. Yes, it is positive. So that is the minimum, and something just went wrong there. A whole bunch of stuff spat out that shouldn't have spat out yet. So that is, in fact, a minimum. So I can go ahead and say, all right, that answer is cool. That's my minimum dimension for x. And then what about y? Well, y is 200 over x. So if we plug 200 in, we'll get 13.86. So those are my two dimensions that give me the least cost. And then the final question is, what is the actual cost? What is the actual cost here? That's where we can go back to our cost function here and plug in our x value of 14.43. And when you work out that arithmetic, you'll get that the cost here is $4,156.92. $4,156.92. Now that is not the minimum material, but it is the minimum cost with these restrictions. Change these numbers in any way, and you're going to change the overall problem, which will change the overall cost. Okay, these are not the optimal dimensions. In fact, if we go back to the problem from before, optimal dimensions actually had x being smaller than y. And that kind of owed to the fact that you used up more x's in the perimeter than you did the y's. But now, x is actually the bigger one, because when it comes down to a cost, x has a factor of 144, y has a factor of 150. Y is more costly to the cost, the overall cost. A bigger y is more costly, so that's why y ended up being smaller than x. And of course, these are all gravitating around that perfect square, which would have been the square root of 200. They're kind of both centering around that number. Okay, so that's optimization. If you find you do have problems or anything, please feel free to ask me. In the notes, you have a problem very similar to this with some somewhat different numbers that's actually tied to a turn-in assignment as well. So be sure to check that out in the notes here on optimization.